I guess we'll go ahead and start. I'm not even going to say my name because it's up there in giant letters. This is a great, having a screen this big, you guys will actually be able to see the code. I'm wearing my Influx shirt, and I was going to take my speaker shirt off and do it in my Influx shirt, but now I have this headset on, so I can't. So you'll just have to watch me sweat. So the whole purpose of doing what I'm doing here is really for building digital twins. And I don't know how much you know about digital twins, but the idea of a digital twin is that you build in software and data a model of the physical system, and you build that model with live data from the physical system, right? So that you can model things like a jet engine in software, and you can make slight changes to it, and you don't have to do it while you're flying around and the plane falls out of the sky. I am really a fan of them doing it in software and not doing it on the plane that I'm on, right? So the whole idea is to be able to take all of these measurements from the Internet of Things, you're instrumenting everything, and be able to do, models with it in real time, right? So I'm going to do some that are basically environmental models. So we're going to work with things like gas. Gas is actually pretty easy. How many people here know about ideal gas law? Right? All right, 2 hands went up. Awesome. So the idea of ideal gas law is that when you're measuring the concentration of a gas in a confined space, you have to compensate that for the temperature and the pressure. As the temperature goes up, you have to compensate your concentration model based on those other 2 parameters. It's a fairly easy calculation. It's really quite easy to do, right? I don't know if here in Europe you get this on your news when you hear the weather, the heat index. Anybody heard of the heat index, right? It's 98 degrees, but it feels like 104. Where I come from, that's kind of every day. I live in the south of the US, and it's always like that. And you can see that it is not simple. In fact, it takes all of this and then some in order to calculate the heat index. The heat index is basically a function of the temperature and the humidity. But then some nutcase went and came up with this really, really complicated formula that you use to calculate it. And you have to calculate the first one, and if that's not right, then you calculate the second one, and if it's between certain temperatures and humidities, then you do a third calculation and subtract it. Otherwise, you do a fourth calculation and add it. Otherwise, you just go with this, right? Sounds simple, right? Easy, not a problem. There are a lot of other things, especially if you run a greenhouse. I hear this from greenhouse growers. They are very interested in things like air density and dew point, and especially the vapor pressure deficit. These things cause bad things to happen to your plants, like they mold, right? So they monitor these things all the time, and it turns out that calculating them is really hard, especially in real time, right? So what I'm doing then is building these models so that I can calculate them in real time, so that I can basically build a digital twin of my greenhouse, right? I want to be able to do all of these things so that I can model what changing the temperature by 2 degrees, or changing humidity by 1%, or the temperature or the pressure. So I know what will happen in my greenhouse without having my plants rot and say, oh, okay, well, that's what happens. My plants rot. Maybe better luck next time, right? So since I work for Flux Data, you can see it under my shirt here, I do it in our data query language called Flux. So let's talk a little bit about Flux. Has anybody heard of Flux? Even more hands than have heard of ideal gas law. That's good. Flux is our new query language replacing what we used to use, which was called InfluxQL. And Flux is much more powerful, much more flexible. You can do all sorts of things with it. You can add to it, you can contribute to it, you can add functions, you can share functions with your friends, you can pass these things around. So it's much more powerful. One of the things that it allows you to do that you could not do in InfluxQL is math across measurements. And that becomes really important when you're doing things like these digital twins, right? I'm calculating the heat index, and one sensor is collecting the temperature and it's storing it into a certain measurement, and another sensor is collecting the humidity and it's storing it into a different measurement. In InfluxQL, you were just out of luck, right? You couldn't do that math calculation. You couldn't have all this fun. Now you can. So I'm going to talk about some terminologies before we get into Flux, because Flux is going to look a lot different. First of all, we store our data in buckets. You've probably heard of this from an S3 bucket, those sorts of things. So we store all of our data in buckets. And that is a named data source, and it has a retention policy. So I can set the retention policy on that to be whatever I want, however long I want to hold on to that data. And I may not want to keep it forever. One of the nice things is that I can set a retention policy, and after that amount of time, the data just goes away. Right? So I don't have to go in and purge old data. I just set a retention policy for, say, 60 days, and any data that's older than 60 days just goes away. We use this thing called a pipe forward operator, which you'll see, and that's how we sort of chain together different functions in Flux to pass the results of one thing to another thing. One of the things that's different in Flux is that all data is returned as tables, which is actually really good because a lot of us are used to working with tables with things like traditional SQL databases and Excel. Everything's in a table. So now everything that you do in Flux comes back as a table, and you can do math on those tables, right? And I'm going to just gloss over the group key because we're not going to use it. So here's a really simple Flux example, right? And it's going to use all the things we just talked about. I'm getting my data from the telegraph bucket, and I'm starting with a range. I cannot emphasize how important it is to always have a range be your first thing, okay? Unless you have about a 30-second data retention policy, have a range. Because if you don't have a range, what you're telling it is, give me all the data. And if you have a lot of data, what's going to happen is you're going to crash. You will hit out-of-memory errors, and away you will go, right? I'm going to filter that data through a function. I'm looking in the measurement CPU and the field for usage systems and the tag CPU, and I want the CPU total, right? And then this last call is to yield. And if this is all I'm doing, I can actually ignore the yield. It will be implied, and it will yield a graph for me in my front end, and I can see the results of that. Otherwise, I can just see it as a table, right? If I'm pulling back multiple tables, then I'll want to have different yields so that I can see the results of each one of those tables. Okay, I promised you math. So I'm going to build a table called CO2 raw, right? And I'm going to look in my telegraph bucket. I'm going to give it a range. I'm going to filter it for the measurement I want. I happen to be doing this live right now. I have a K30 SenseAir CO2, industrial CO2 sensor. And I'm storing it in the field CO2. I'm doing an aggregate window. We'll talk about the exists later, right? With that, I'm going to filter out any rows in the table that have no value because I don't want to do math on a no value. That doesn't end well for anybody. I'm going to keep a couple of values, and then I'm going to yield that as a table called raw CO2. Wait, there's no math in there, is there? Right, we'll get to the math. So here's the table that builds. And you can see it's called raw CO2 up here, right? And it's a table 0, there's my values, and there's my timestamps. right? And if we go back, you'll see that I told it to keep the column's value in time. I wasn't interested in any of the other stuff that came back. None of the other tag values, nothing else. I only wanted those 2 columns. So now I've basically got a 2-column table. Great. So let's build a couple of more tables. What am I doing here? I'm getting ready to do the ideal gas law calculation. So I'm going to build a table for the temperature, and I'm going to build a table for the pressure. And you'll notice that I'm pulling them out of 2 different measurements. So now I've pulled values out of 3 different measurements. I've built 3 tables out of 3 different measurements. If I were trying to do this in FluxQL, I would have been done a long time ago because I couldn't do it, right? Only 1 table. I only want 1 table. So I'm going to do a couple of joins. Anybody who's been doing SQL knows about joins, right? So I'm going to join the first 2 tables, and I'm going to join them on time because I want my measurements to align on time, on the time value. We're talking time series data. Makes sense, right? Then I'm going to do a second join, and I'm going to join that first table to the second table. Now I've got a single table that's got 3 columns. And I'm going to name the columns time, pressure, gas, and temperature. So I've got a table that's got all the stuff I need, right? And now I'm going to do the math on it. I don't know if you can see it down here with the spotlight. Ideal gas law. Boom, done. Magic. I told you we were going to do math. We'll see how I do the math in a minute. But I've now done a calculation, a fairly simple calculation on measurements, 3 different measurements in real time. So here's the ideal gas law calculation. I put it in a library called environmental. You saw the call here to environmental.idealGasLaw. I built a little library for myself so I didn't have to have ugly math in here, right? I could hide all my ugly math here. And so this is in an external Flux library, and I've built something called Ideal Gas Law. It takes tables in and it puts tables out. And here's what it does. It goes through and it maps again time to time, and it's going to return a single column called underscore value. And that is equal to gas times temperature plus, on and on and on. Ugly math, right? And I will get back a table that has 2 columns, time and the ideal gas law calculated value based on CO2 concentration, temperature, and pressure. And it looks like that. So now I can do this in real time in the front end, in the UI. I don't have to go do the math and store another value in my database for the ideal gas law calculation, right? I can just do it in real time. And I can put them both on a graph, and I can see that the blue line is the raw CO2. It was about 1,300 parts per million, and compensated for temperature and pressure was about 1,400 parts per million. You don't really want to be doing anything serious in a room with that much CO2 in it. Anything over about 1,000 parts per million, and human decision making is compromised. Okay. I will also add that I have almost never been in a meeting room in a company where the CO2 concentration was below 1,000 parts per million. You can draw your own conclusions from that. But I take this little thing with me to almost everywhere I go because it's battery operated and it's small, and I can turn it on and I can put it on a table, and it will begin shoving data into my database, and I can see how bad our decisions are. So I can add more stuff to my environmental package as I go, right? And then I'll be able to share that package with others. Right now in the early version of Influx 2.0 that uses Flux, we don't have that ability to share packages out yet. It's coming real soon. So right now I have to actually compile my own version of Flux with this in it. So I just do that, right? So I told you that we were going to do some serious math. So this is some serious math. So as I said, this is in my external library. And you'll see why I hide this, right? Because there's the Steadman equation, which is fairly straightforward. And then there's what's called the Rothsfuz regression. And then there's a required adjustment number 1, and there's a required adjustment number 2, right? And that's why. Because what I have to do is take those values, temperature and humidity, and I've got to do the Steadman equation on them. And if that is less than 80 degrees, and I average that with the last temperature value just to make it more fun, because that's what they tell me to do, right? And if that average is less than 80 degrees, then I'm good with the Steadman, and I can just go home. Chances are, if I'm actually calculating heat index, it's probably warmer than that. So if humidity is less than 13% and the temperature is greater than 80 degrees, then I got to do the Rothsfuz regression and subtract out that first adjustment, right? If it's greater than 85, right, it's a nightmare. So you can see why I have hidden all of this into a simple function so that I can just call heat index with a table with my humidity and my temperature and get my result back. And I now have a graph that shows me the temperature and the heat index. Fairly straightforward. How many people want to see a demo? Awesome. Come on. Come on. Oh, my mouse is all the way over there. I gotta find my mouse here, guys. And you can't see that. Is that coming over? Oh, it goes the other way. Outstanding, that makes sense. All right, now I gotta try to drive from up here. So I'm calculating the CO2 raw value and the compensated value in real time. And if I blow on this and we give it about 15 or 20 seconds, we should see it spike. The reason I'm giving it 15 or 20 seconds is because it's much more efficient for me to batch up my data writes from this little device and write 5 or 10 of them at a time. So I take a reading every 2 seconds because that's all the sensor can handle. And every 5 or 10 data points, I write it all out. Oh yeah, there it went. What are we at there? 2,500? 5,000, awesome, real time. I'm doing the heat index calculation in real time down here. And I'll show you this little bit that's not in my talk, but is pretty cool. That's the temperature over there in the far. So it's what, 30 degrees in here? It's a little warm. But here's some really cool stuff. I can see some other data about that sensor. Now, where did I get that data? One of the things that's really important with IoT is not just the data coming out of the sensor, but the metadata about the sensor, right? When was it deployed? Who owns it? How do we get in contact with that person if something goes bad, right? So it turns out that with Flux, I can do something really cool. So I'm going to get the temperature, right? And I'm going to set a couple of secrets, my SQL user and my SQL password. And from this calculation, I'm going to pull out something called the sensor ID. So my sensor is writing only really one tag value. It's writing the temperature and the tag value to the database, to the time series database. And I'm going to go and I'm going to grab that tag value, and I'm going to put that tag value into a SQL query. And I'm going to query a MySQL database where I have all my metadata about all my sensors using that tag value, because I want to know about that sensor. And I'm going to get back a table and then I'm going to join that table with my actual sensor data on that sensor ID, and it's going to build me this nice table of the address and the customer and the class of the MCU of the microcontroller it's running on, and the vendor that I bought the microcontroller from, and the manufacturer of the sensor, and the temperature. So now I can actually pull together my metadata from my MySQL database with my sensor data and pull it all together. And if I really wanted to be fancy about it, I could pull all that together and do the heat index calculation, and I could put it all in one table. You couldn't do that with InfluxQL because you couldn't query a SQL data. I could have stored all of this stuff as tag values in my database, but tag values really aren't the place to put data like metadata about your sensor, right? I don't want to put a customer's name and address in my time series database as a tag value, right? I'd rather have it in my customer database where I already have it and just be able to query it and add it in and put it on my dashboard here. I can show you I'll comment out, and we'll view this as just the raw data. And you can see, here's my results that is really just one row of data from my SQL database, right? So the raw data is actually the table data that's coming back from all the sources. And I can query data from multiple sources and get multiple tables, and then I can join those tables together into one result with Flux. This is what's going to allow me to do things like digital twins, where I can synthesize all of this data from multiple sources and bring it all together so that I can see it all in one place. And I can make changes to the data and see what happens. I'm doing some other stuff down here that we didn't talk about. I'm actually calculating the vapor pressure deficit and the dew point and the air density. You'll notice that the dew point and the air density are inverse calculations of one another. So I've basically got my greenhouse managed in this one dashboard now. I can see all the stuff I need to see about my dashboard. The library that I've built for this has a few other things. It does the wind chill because that's something that some people want to know, but it doesn't do a whole lot of good for me to travel with an anemometer because there's really not a whole lot of wind movement in here unless we all blow really hard at once. So I tend not to travel with that. Right? Now I got to get my mouse back. So just for fun, I grew up in a weird family. This was something that my mom used to say. I'm not making that up. My mother was a computer scientist. All of this is going to be available. So I have a slide of resources where you can read up on how to calculate ideal gas law, heat index, all the documentation on Flux. And the last link down here is a bit.ly link to the slides from this talk. So you can go and get that as well. And I believe it is question and answer time or more demo time if you want to see me do stupid Flux tricks. Any questions? None? Wow, yes. I'm not sure I can mention companies that are using Flux. So one of the things that we have done with the rollout of 2.0 is we have basically two versions of it. We have our open source, which is free open source, and the open source for the 2.0 version is actually still in alpha. But we have a cloud version of it, which is now generally available, and we actually have brought up a version of it in a data center here in Germany. And we have a free tier for it. So you can go to cloud2.influxdata.com and sign up for a free account and start using that to send data to calculate data on. In terms of customers, I'm not sure, I just don't know how many of them are using Flux at this point. We have a lot of people starting to move to Flux because of the power of the language and what they can now do with it. If you're a 1.7 InfluxDB user, you can actually go into the configuration file in 1.7 and turn on the Flux language, and then you can use the Flux language against the 1.7 version of the database. So Flux language is enabled in 1.7 and above in InfluxDB. All the stuff I'm doing is in the 2.0 alpha stuff. So I'm actually running my own version of the database in a data center back in the United States. And these sensors are sending their data back to the United States, and then I'm doing the queries in real time back here and displaying them here. So it's pretty efficient, and it has not so far put any extra load on my server. I happen to serve about a dozen domains off that server as well, and none of them have complained that I'm also running this database, which has been collecting data now for since I believe it was March. So there's a fair amount of data, historical data there as well, and it so far has had pretty much zero impact on anything else I'm doing. Other questions? Yes. Not very much. I mean, I also run it on my laptop here. I run it on a couple of Raspberry Pis at home. Raspberry Pi is easily powerful enough to run it. just depends on how much data you want to store. This little sensor is, the CO2 sensor itself costs about $100 US just for the sensor board. It's a fairly robust CO2 sensor. To backtrack a little bit, you can go to Adafruit or any of these vendors and you can buy the sort of the $5, $10, you know, it's called eCO2, and everybody says, oh, they're close enough. They're not even close to close enough. So when I'm running this sensor and the eCO2 sensor side by side, the eCO2 sensor is off by at least a factor of 2, sometimes as much as a factor of 5. So if you breathe directly on them, it'll spike and it'll be pretty close, but it drops right away back down to its baseline, which is 400 parts per million. And the CO2 in almost any room is well above 400 parts per million. So if you're serious about CO2 measurement, get this one. And I built the rest of it myself. So there's 2 lithium-ion batteries and an ESP32 board in here to run it all, because it turns out that you need a fair amount of power to run the sensor. And do not, take my advice, do not try to run it off of any Arduino board. It will eat the power supply in somewhere under 10 seconds, and you will never get the board back. And I have a pile of them that can attest to that. Because I did not read the directions, and then when I did read the directions, I did not believe the directions. So read the directions and believe them, because it will. This is just a temperature, pressure, and humidity sensor, Bosch BME 280, which is, you know, a couple of bucks. And then I also put a light sensor in there so I can tell how much, you know, how much light I'm getting from the spotlight. And all of these, again, are sending data in real time while I'm standing here, and I can go and look at it and graph it in real time. Other questions? Yeah. A good sound sensor. I have not done any sound sensing yet. That's not been something that I've mostly been doing sort of environmental stuff. So I've got most of this same setup outside of my house, so I can do outside versus inside. And I've got an anemometer there so I can do wind chill and other stuff, because that's where it makes sense. But I have not done any sound. I'm pretty sure that you can get sound sensors for fairly cheap at most of the online vendors. They're pretty cheap. I build all my own sensors, so you know, my own devices. And if you follow me on Twitter, then you'll see most of my hardware projects go through there, and I write them up complete with where I bought everything, how much I spent on it, how to put it together, how to solder it, where the software is, how to, you know, the whole thing. So it's pretty easy to do. And I generally try not to say things are easy, and I have a really hard time with that with InfluxDB, especially with the version 2, because there's not a whole lot of installation, there's not a whole lot of configuration. With the open source version of InfluxDB 2, you download the binary and you start it. And then you go to the web page that it tells you to go to, and you fill out the pieces of the form, and it starts and it runs, and then you can start writing data to it. It's sort of alarmingly simple to run, and that's not by accident. Our CTO has had us trademark the phrase "time to awesome," because he's very focused on making the tool useful and out of the way. So you don't spend all your time trying to make Influx do something. You're able to use it to do what you need to do, to get the answers you need to get, to store your data, to manipulate your data, to display your data, rather than spending all your time trying to configure the database and configure the front end and make sure that it all works, right? So it just sort of works. Yes? Yes. The limitations are, first of all, you only get a 72-hour data retention policy. So you can't keep the data around for very long. I'm not quite sure off the top of my head what they are. There are some limitations on the amount of data that you can write in the writes per second sort of levels. And then for doing alerts, there's only one of our alert levels, and that's an alert to Slack. So you can alert to Slack, but anything other than that is a paid. And one of the nice things about the 2.0 cloud is also it's pay as you go. So you can increase your data rates, and you can pay a little bit and you get to do a little bit more, and you can pay a little bit more and get to do a little bit more. It's not like you have to buy, a giant package in order to do it. Yes. I don't know the answer to that, actually. Please do, and I can connect you to somebody that can answer that for you. Yeah. One of the things that I am not showing because it's too hard to travel with is the ability to do alerts. So actually, all of this data is I'm running some alerts. So the database is actually going to be writing out about every 4 seconds, there it is, the last CO2 reading to an MQTT broker. And when I'm near home, I have a giant globe that's about this big that's full of colored LED lights, and it changes color based on the concentration of CO2. So if I breathe really hard on it, it turns bright red, telling us that we should get out of the room. But it's a big glass globe, and it doesn't travel internationally very well. But I can tell you how to build one. They sell them at IKEA for something like $10. And then you rip the insides out, and you put some other stuff in there, and you can make an alert so that it will let you know what the CO2 concentration is. See, 564, that's pretty good for indoors. I was giving a workshop in Spain earlier this year, and we were in a small below ground room with low ceilings and no ventilation, and at one point our CO2 concentrations hit about 6,500 parts per million, and people were literally falling asleep at the table. I told myself that I just wasn't boring them to death, that I was slowly poisoning them with CO2 instead. So there you can see it spiked to over 6,000. And that's the database that's actually writing those out. So I'm using that as an alert mechanism. I'm using MQTT as an alert mechanism. And that's actually now built into Flux as well. So that, remember how I showed that I could do input from SQL, I can do output to other sources as well. So I can write output to MQTT, I can write output to SQL, I can write output to other data syncs. Other questions? I'm blinding myself with this. Yes. Yes. There are no restrictions on the open source version other than you can't cluster it because there's no clustering and high availability layer for it. So you can run single node versions of it, yeah, as long as you want. That's free open source. And you can run as many of those as you want. When you want to start, if you want to build a cluster, an actual cluster with failover and high availability, that's our enterprise license. Yeah. Other questions? Well, I think I'm standing between you and a snack, so I will let you go. Thank you very much.